Is Pingal, Pratyush, Nath. So he'll be talking about certified randomness from temporal correlations.
So hi everyone, I'll be talking about the certified randomness from temporal correlations. This is based on our recently published work with Professor Devashish Saha, Dipankar Home, and Professor Urvashi Sinha, and also some current work going on with Aninda and Urvashi. So the question of generating randomness from scratch, or whether there exists some fundamental random processes, is very important for our understanding of nature. But if you leave these questions aside, random numbers itself are a very useful resource. They can be used in all sorts of applications, starting from statistical sampling, simulations of complex physical and biological processes, weather forecasting, etc. And moreover, if you are into like card games or maybe tried your luck at a casino, you know that you need some sort of randomness to keep things interesting. Now, the random numbers that are used for these applications doesn't need any certification or privacy. So what I mean to say is, you don't really have to worry about whether someone else has information about your random numbers, or whether someone else can replicate the process that you use to generate these random numbers. But this is not the case for critical applications such as secure communication and cryptography, where the secrecy of your messages completely depend on the random numbers. So this opens up a really new line of research of identifying processes and certification tests for random numbers. And to motivate this further and establish something which is known as device independence, I will, in the next couple of slides, I will show you some examples of the most common type of random number generators. The first one is something known as the pseudo-random number generator. So now if you ask Python or Mathematica to give you a bunch of random numbers, this is what it does. It uses some sort of recursive relation like this, where A, C, and M are the parameters. And M here gives the range of numbers that you want. And A and C are set by the number of random numbers that you want to generate. Now if you have a look at this, let's say if you start with some initial x naught, you will find this can generate a really good random number. But the problem with this is, once someone knows the formula that you're using and these parameters, this set of random numbers is totally determined, and it's not really safe for use in secure applications such as cryptography. And this, because the security is completely dependent on the complexity and the initial seed of this algorithm. Why I'm saying complexity is because unlike this, there might be some formulas which are really difficult to compute, and in that case you get some time frame in which you can use the random numbers. The second type of random number generators are called true random number generators. So unlike the last one, which is based on some mathematical formula, here you use some proper entropy source. For instance, let's say you're working on a computer and the computer might record your mouse movements, and then it can process it and generate a random number from there. Similarly can be done with fan speed of a computer, atmospheric noise, temperature fluctuation, etc. And one very important example is a quantum random number generator, where let's say if you measure a superposition state and you do measurements on it, these are supposed to be random. But the problem with this is, but this is a really big problem which I'm going to explain with this example. Let's say someone sold you a true random number generator, saying that it has a bunch of qubits which, if you let's say give some input, it will be created in some equal superposition state, and you get a bunch of really nice random numbers out of this. Now the question is, how do you certify that these are coming from a truly random or a truly quantum source? It's really difficult to have a look at these numbers and say the authenticity of the source. You can do some statistical tests and see how widely this is spread, but there is no way to certify its source. So Pironio and Essin in this really famous paper showed that it can be possible to certify the device, these random numbers device independently, by violation of the Bell inequality. So let me show you how this is done. So I don't really have to introduce Bell inequality here, but as a refresher, Bell inequality can be derived from the conditions of locality and realism. Locality follows the usual definition, if you do something here, it won't affect something very, very far away. And realism is the property that objects have definite properties without measurements. And this is the most famous Bell scenario, which is called a 2-to-2 scenario, because you have two measurement stations, and each measurement station has you have two systems, and each system has two measurements, and the outcomes are also like two. And the most famous inequality is the CHSH inequality. So if you combine these probabilities and use these conditions, you can show that these whole expression doesn't exceed 2. And we know that quantum mechanics violates this inequality with a maximum violation of 2 square root of 2. Now these are ontological conditions, meaning that you cannot prove these things in experiments. So, but Bell inequalities can also be derived from some really practical conditions such as predictability and no signaling. So predictability is a condition that, like, if you do some experiment, the probabilities for all these scenarios, if it is either 0 or 1, then the process is called predictable. And no signaling follows directly from special relativity. So like if you place the systems really far away, the measurements at one system is not affected by what you choose to measure on the other side. And if you use these two conditions, you can get this factorizability relation, and from here Bell inequality follows. So now, if you do an experiment that violates Bell inequality while satisfying no signaling, then it means that predictability is being violated, which means that the outputs are random. Now, this is a really foolproof method to produce device-independent random numbers, and a lot of work has followed along with experiments. But this has one very big problem. It's that in order to ensure no signaling, you have to place the two systems really far away. And these are some of the, like, there's a long list of experiments, and I picked up some of them. And here, if you see, the measurement station should be placed at least around by 200 meters. And this was really beautifully pointed out by one of the authors of the paper, Pironio, that no matter how hard you try, you won't be able to reduce this distance. And so we have to think of some new ways of generating and certifying randomness, and our work is basically inspired from this. And what we did was we found a protocol, we devised a proof of protocol and implemented it, which doesn't require this distance verification. So let me show you how this is done. So now the Bell inequalities are based on special correlations. One can also think of deriving inequalities based on temporal correlation. So let's say if you have a system and you measure it at different instances of time, so the probabilities that you get from these systems might also violate some things. And these type of inequalities are first proposed by Leggett and Gerg, and hence they're known as Leggett-Gerg inequalities. And they're derived from some similar conditions of realism and non-invasive measurements. The concept of realism is similar to that of realism in the Bell scenario, where let's say if a system has multiple states, then it has to be neither one of these states. And non-invasive measurement says that it is possible to determine the state of the system by doing some slightly infinite perturbation or measurement in the system. And if you use these two conditions, you can derive LGI. So we can like think of it in the following manner. Let's say if you have a qubit, and U1 is a unitary operator that takes you from T1 to T2, and U2 takes you from T2 to T3. And you can choose to measure at these times T1, T2, T1, T3, and T2, T3. And if you calculate this correlation, where these correlations are defined in the following manner, you see that like using the conditions of realism, you find that this cannot go beyond 1. But we find that quantum mechanics violate this with a maximum violation of 1.5. Now, similar to the Bell scenario, Leggett-Gerg inequalities can also be derived from the conditions of predictability and no signaling in time. So predictability is similar to what was described in the Bell scenario, whereas no signaling in time is a new condition. So what it says is, like, if you measure a system at different points of time, the measurements at a later time the outcome at a later time shouldn't be affected by whether you choose to measure it at some earlier time or not. So here, let's say if AI is the earlier measurements, and if you sum over this should be equal to this. And for the 3 times scenario, these are the 3 no signaling in time constraints. Now it is important to point out that unlike no signaling, which is constrained by which comes from special relativity, this doesn't have to be satisfied, but you can design experiments in which this thing is satisfied. And so from here we can see, like, if we do an experiment that violates this Leggett-Gerg inequality and satisfies the no signaling in time constraints, then our outcomes will be predictable. Outcomes will be random. So the first thing we did was to derive the sum. So was to quantify the genuine randomness that we got from this experiment. And so in order to quantify it, we used the minimum entropy, where like we maximize this. We use the maximum of this probability for all the possible scenarios. The intuition is really simple because the maximum probability will give you the least amount of randomness. And in order to derive the bound, we solved this optimization problem, where we maximized this P over all these possible choices of inputs and outputs, with the constraints that the Leggett-Gerg inequality is this, and the no signaling in time conditions are satisfied. Now for a Bell scenario, you can convert this into a semi-definite programming problem and solve this exactly, but it's not possible for this temporal scenario. So we have to take some assumptions. The first assumption is that we're using a two-dimensional system or a qubit. So in order to enforce it, we use this general definition of rho. And this also goes well with our experiment because there we use the path degrees of freedom of a photon to do the experiment. The second is that we are using projective measurements at the first times and the general measurements at the last. And this also goes well with our experiment, which I'll show later. And the third assumption is that the initial state we are using is not correlated with any other thing. So this is a very dangerous assumption, and we don't like this, and we'll try to, and we will like remove it in the further discussion. And it is possible to solve this problem analytically with these assumptions, and we find this bound where alpha is kind of related to the Leggett-Gerg inequality violations. And we see that this genuine randomness increases monotonically with the inequality violation and reaches a like value of 1.4. Now this type of behavior is also seen in the Bell scenario. Now, like I said, like it's a really dangerous assumption to assume that the initial state is correlated with some other state, maybe of the eavesdropper. For example, yeah. So what we do is like we discard the first output and we use conditional probabilities and solve the same optimization problem, and we get a very similar bound. But here it goes to 0.4 instead of 1.41. The red points here are the numerically the points from numerical simulation. And we also wanted to check what happens if these NSIT conditions are violated slightly. And we don't know whether we will get random outputs from there or not. Now it's really difficult to solve this problem analytically, so we solved it numerically. And we found that for small violations of NSIT, we still get randomness, but these random numbers start appearing only when the LGI violation increases. So this is a very important result, and we are looking further into it. And we also like curated our results to take into account the memory effect. So what is a memory effect? So in order to do this type of experiments, you have to do it multiple times, and there might be scenarios where the system is influenced by some earlier measurements. So we use statistical analysis and the properties of martingales to find this epsilon correction, and this epsilon is given by this, where n is the number of runs, IQ is the maximum LGI variation, and Q is the probability with which you choose the measurements. And here we find that like this is the line for no memory effect, and this is for memory effect. So in the presence of memory effect, we get less randomness. And also we see that like if you choose the input settings like with some biasness, then you get even lesser. So yeah, so I won't go into details of this, but so this is just to show that we did an experiment and we generated random numbers. And secondly, the most important thing is this is loophole free, and it's yeah. So we conducted around 1,000 runs of this experiment, and we got an LGI variation of 1.32. So the device was tuned in such a way that the expected value was 1.34, but we got slightly less. And these are the three NSIT conditions are satisfied up to a tolerance of 10⁻². And there were 8 parts of the experiment, and we generated different lengths of the random bits at different rates. And the final result was around like we generated 9 lakh random bits at a rate of 3865 bits per second. The further work is implementing this same protocol on superconducting quantum computers. So we have used the IBM quantum computer to implement this, and the problem can be like curated in terms of gates. So this is one example of a circuit. And this is one plot where I have shown the LGI violations of the experiments that were run in this computer. So the important thing is, like, you see, these are really close to the LGI violation expected. So the effects of noise are very less, and they can also be simulated to show like why this is slightly low. So the conclusion, so I've showed that you need device-independent random number generators for secure applications, and Bell scenario, although it provides a really foolproof method, but it has this distance barrier. And what we did was we used temporal correlations to overcome this distance barrier and generated secure random bits. Thank you.
So thank you, Pingal, for your wonderful talk. So we can have.
Yeah, so I don't quite understand the no signaling in time. So no signaling in space, I know it's trivial.
Yeah.
So, but when you say that, there can't be a signaling from, let's say, quantum states at T1 to some future time T2, so doesn't it depend on what unitary evolution the state is subjected to?
Yeah, so like I said, it shouldn't be true for like all scenarios, but you can devise some scenario in which the initial measurement will not affect the results of the final measurements. And it doesn't come from any fundamental principle like no signaling.
Okay, but suppose you use some unitary evolution, you subject to quantum state to some evolution and then generate random numbers. So looking at the sequence of random numbers, isn't it possible to back calculate what unitary evolution you should have subjected?
It's not possible.
Okay, thanks.
So if we don't have any questions, so maybe we can thank Pingal again.